Patty Simpson with Simpson Math. In this video, we're going to introduce the empirical rule. So we looked at the normal curve in a previous video, and we talked about the fact that the normal curve is a symmetric bell-shaped curve where we are describing a continuous variable. Here I have some notation. This notation says that we're going to draw a normal curve with a mean of 18 and a standard deviation of 1. So remember, that means that we're going to look at a normal curve. The mean is 18 and the standard deviation is 1. So we're going to look at this probability density function that has a mean of 18 and a standard deviation of 1. And I'm going to draw that here on my graphic. So the mean is right in the middle. In that symmetric or bell-shaped curve, our mean, our median, and our mode are about in the same spot. So our mean is right in the middle. And then our standard deviation tells us the distance from the mean. So that distance is 1 unit away. So I'm going to count by ones. So I go from 18 to 19, from 19 to 20. This 19 is 1 standard deviation above the mean. The 20 is 2 standard deviations above the mean. And 21 is 3 standard deviations above the mean. If I go backwards, 17 is 1 standard deviation below the mean. 16 is 2 standard deviations below the mean. And 15 is 3 standard deviations below the mean. Now we know that this normal curve is a bell-shaped symmetric curve. And so my mean, my median, and my mode are going to be at the same spot. So it's going to be the peak of the distribution. Then my 17 and my 19 are going to be symmetric. So wherever that 17 is, the 19 is, if I fold it here, those two should match. Then the same thing is going to be true with my 16 and my 20, and then also with my 21 and my 15. We also looked at it in a previous video that our normal distribution has this asymptotic behavior. In other words, it's going to get closer and closer to that line there without ever reaching it. So my curve, my normal curve looks something like this, where I have that nice peak on the top. At that standard deviation, we call this an inflection point, where we turn from concave up to concave down. So this kind of turns my graph, and then it twists around, getting closer and closer to that asymptote without ever reaching it. Then I should be able to draw a line, and it should do the same thing on the other side. So my normal curve looks something like this. And we call that, again, an inflection point. Inflection point. There's my peak on that graph. Now, we also learned in a previous video that the area underneath this curve, because it is a probability density function, the area under this curve is equal to 1. So if we were to be able to do some calculus and look at the integral of that particular function, we would see that the area underneath the curve is 1. Well, luckily some people know a little bit more about calculus, and they've been able to find out the area under certain places in the curve. And we're going to look at that here in just a second, called the empirical rule. I'm going to go ahead and draw this one as well. This is also a normal distribution. My mean is at 12, and my standard deviation is at 1/2. So when I get ready to look on my number line, my mean goes in the middle again. And now, instead of counting by ones, I'm now counting by halves, because my standard deviation is just 1/2. So from 12 to 12.5 to 13, this 13 is 2 standard deviations above the mean. And then 13.5 is 3 standard deviations above the mean. Counting backwards, I've got 11.5 is 1 standard deviation below the mean. 11 is 2 standard deviations below the mean, and 10.5 is 3 standard deviations below the mean. Then again, my 12 is my mean, so my peak will be there. At 11.5 and 12, these two are symmetric, so the points will be symmetric. My 11 and my 13 are also symmetric, and then out 3 standard deviations, my points there are symmetric. So then I just draw my normal curve so that at that inflection point, we turn, and then at the next one, and it gets closer and closer without reaching it, continues forever. And the same thing is true here, where it hits and it continues forever and ever that direction. And again, we know that the area underneath this curve is equal to 1. Well, if we use calculus, we can find the area between certain parts of this curve as well. We could look just between 19 and 20 and see what the area is. Well, we know if the area under the whole curve is 1, then this piece will be less than 1. And that's how it is with each piece in here. They're less than 1. And we have something called the empirical rule. And the empirical rule tells us, that within 1 standard deviation from the mean, so in this case from 17 to 19, in this case from 11.5 to 12.5, within 1 standard deviation from the mean, that area underneath the curve, so this area from 17 to 19 makes up 68% of my distribution, or that area is 0.68. So 1 standard deviation, within 1 standard deviation, is 68% is 68% of my curve, or the area is 0.68. So that means, remember that probability and area are related. Remember when we would spin our spinner, and if the wind part was 1/4, and we knew that the probability we landed there was 1/4. So the probability that I get some data point between 17 and 19 is 68%, since this makes up 68% of my curve. So always between 1 standard deviation is 68% of the curve. Then within 2 standard deviations, so in this case between 16 and 20, or on this one between 11 and 13, so between 2 standard deviations makes up 95% of my data, or this is 95% of the curve. So the area under the curve here is 0.95, or 95%. So let me write that down. So the 2 standard deviations, within 2 standard deviations is 95% of my curve, or 95% of the area is there between 2 standard deviations. Then out 3 standard deviations, which you can see out 3 standard deviations, it gets out beyond that, it just tapers off. So there's very little out on the edges. Most of your curve is there. So out 3 standard deviations is 99.7% of your data. So within 3 standard deviations is 99.7% of that curve. 0.997 is the area underneath that curve. So the empirical rule tells us this 68, 95, 99.7. Within 1 standard deviation, 68% of your data is going to fall, or you could say 68% of the area under the curve. Within 2 standard deviations is 95%, so 95% of your data lies within 2 standard deviations, or you could say that the area under the curve within 2 standard deviations is 95% of your curve. And then with that, in 3 standard deviations, it's almost all of your data. There's 99.7% of your data in a normal distribution is going to fall within 3 standard deviations. In the next video, we'll practice finding some probabilities based upon this empirical rule of 68, 95, 99.7. Math Made Simple is some math. Thanks for watching.